In this video, I'm going to evaluate the divergence of a vector field called F, where the vector field F in this case is equal to angle bracket e to the x y x y z to the 4. Okay, so first of all, in order to calculate the divergence, we need to know what this symbol means. Well, this is a vector symbol, so what is this triangle? This triangle is called del or nabla, and the symbol altogether is given by this. Del is equal to the partial derivative with respect to x. The partial derivative with respect to y, the partial derivative with respect to z. So it's a vector operator. It's an operator because it consists of operators, which in this case are partial derivatives, and it's a vector because it has a vector symbol, and we enclose the partial derivatives by these angle brackets. And the vector operator itself takes on the same form as a vector with components. All right. So now that we know what del is, we can calculate the divergence. Here is a dot for a dot product. And when you take the dot product, you multiply components. You add the products of analogous components. So I'll demonstrate that here. In dark red. So for this particular case, the divergence of F is equal to, now let's write what del is, d dx, sorry I'm repeating, d dy, d dz, dot for the dot product with the vector field e to the xy, comma xy, comma z to the 4. Okay. Now we apply the normal dot product operation as if these are just normal vectors. So you have, d dx e to the xy, keep drawing random lines, sorry, plus, so this is where you add in between multiplication, d dy xy, plus, I should probably point to what I'm multiplying here, d dz of z to the 4th, d dz of z to the 4th. And good thing we're using partial derivatives here, otherwise this would be incorrect. We have a multivariable expression, so we should definitely be using partial derivatives. So the partial derivative with e to the xy, well, we treat y as a constant, so you would get e to the y times e to the xy, bringing down that y, as which is a constant, plus, wow, not sure exactly what happened there. Oh, I went to a different page. Okay, so plus x is, in this case, is the constant, so we have calculated this partial derivative, and finally we use the power rule for z to the third. All right, so that is what the divergence of this particular vector field is. If we wanted to know exactly what that vector is, oh no, it's actually not a vector, it's a scalar. Dot products give you scalars. If you want to know what the scalar is at a particular point, you can just plug in whatever the coordinates are of that point. So say we wanted to calculate the divergence of this vector field at the point, say, 1, 0, 2. What is the divergence at 1, 0, 2? I'll write out that question. What is the divergence of f at 1, 0, 2? Then to do that, you would plug in those coordinates. So I would say it is, well, okay, the first term goes to 0 because the y coordinate is 0. The second term is x, which is 1. We have a 4 here, and then a z to the 3. So what's z? It's 2. So 2 cubed is 8. What's 1 plus 32? It's 33. So that is what the divergence is. It's a scalar. 33. And this notion of divergence is helpful in vector calculus. Vector calculus is used in advanced versions of calculus, such as multivariable calculus, but in my opinion, most of calculus is multivariable. All right, I'm going to stop the video now, and I hope that helped you understand the mathematical concept of divergence.